P 2.4 Product Rule for Counting. In this chapter, we have looked at calculating the probabilities of combined events. When two or more events occur, we can find all of the possible outcomes and therefore calculate the probabilities of each outcome occurring. We have done this in several ways: by listing outcomes, using sample space diagrams, using frequency trees, tree diagrams, and Venn diagrams. In today's lesson, we are going to look at the product rule for counting. This is a method that allows us to calculate the number of outcomes of two or more events. To find the total number of outcomes for two or more events, we multiply the number of outcomes for each event together. Remember that in maths, the word product means times. This is where it gets its name from. Let's have a look at a really easy example to see why this method works. Here are two spinners. The first spinner has got 4 equal sections labelled A, B, C and D, and the second spinner has got 3 equal sections numbered 1, 2 and 3. So if the first event is that we spin spinner 1 and the second event is that we spin spinner 2, all of the possible outcomes are as follows. We could get an A on spinner 1 and a 1 on spinner 2, an A on spinner 1 and a 2 on spinner 2, an A on spinner 1 and a 3 on spinner 2, and so on. A B on spinner 1 and a 1 on spinner 2, a B and a 2, a B and a 3, a C and a 1, a C and a 2, a C and a 3, a D and a 1, a D and a 2, and a D and a 3. This method is listing outcomes that we looked at in lesson P 2.1. So a total there of 12 possible outcomes for those two events. Now, if I were to write the combinations in a slightly different way, with the outcomes for event 1 on the left hand side, the outcomes for event 2 on the right hand side, so A, B, C, D, and then 1, 2, 3, we could look at the total possible number of outcomes for both of these events as follows. We could get an A on spinner 1 and either a 1, a 2 or a 3 on spinner 2. There's 3 possible outcomes. Or we could get a B on spinner 1 and then either a 1, a 2 or a 3 on spinner 2, another 3 possible outcomes. We could get a C on spinner 1 and either a 1 or a 2 or a 3 on spinner 2, another 3 possible outcomes. Or we could get a D on spinner 1 and either a 1, a 2 or a 3 on spinner 2, another 3 possible outcomes. So 4 lots of 3 possible outcomes. 4 times 3 is 12, so 12 possible outcomes of those two events all together. The 4 being the possible outcomes for event 1 and the 3 being the possible outcomes for event 2. So now we have seen how this method works, let's have a go at answering some of the questions. Question 1. An ice cream cafe serves 8 different flavours of ice cream, 5 different flavours of sauce, and 12 different types of topping. Part A. how many different ways are there to choose an ice cream with sauce? So the first event is picking an ice cream, and there are 8 different outcomes for that event. And the second event is picking a sauce, and there are 5 possible outcomes for that event. So in order to find the total number of possible outcomes for those 2 events, we simply do 8 multiplied by 5. So there are 40 different ways to choose an ice cream with a sauce. Part B. How many different ways are there to choose an ice cream with a topping? So event 1, picking an ice cream, there are 8 possible outcomes. Event 2, picking a topping, 12 possible outcomes. Let's multiply the outcomes of these 2 events together. And that tells us that there are 96 different ways to choose an ice cream with a topping. Let's have a look at part C. How many different ways are there to choose an ice cream with a sauce and a topping? So this time we have got 3 events: picking an ice cream, picking a sauce, and picking a topping. So this method works for 2 or more events. So it is the same method. We write down how many outcomes there are when we choose an ice cream, which is 8. We multiply this by the number of outcomes when we choose a sauce, which is 5, and then multiply this by the number of outcomes for selecting a topping, which is 12. So we're going to do 8 multiplied by 5 multiplied by 12. There are 480 different ways to choose an ice cream with a sauce and a topping. So it's your turn now to have a go at some questions like these then. Multiply the number of outcomes for each of the events together to get the total number of outcomes for the 2 or more events. Pause the video to copy the notes, to check your understanding and to try the questions from I'm Giving It a Try. Remember to mark your work and reflect on your confidence. Unpause the video when you're ready to try the next question. Question 2. Peggy is choosing a 4-digit PIN for her bank card. Each of the digits can be a number between 0 and 5. So in other words, 0, 1, 2, 3, 4, or 5. Part A. How many different pins can Peggy choose from? So the way I like to tackle questions like this is I like to put a dash for each of the digits in the pin number. So 1, 2, 3, 4, and take each of the digits in turn, working out how many possible outcomes there are for each of these digits. Once I know the number of outcomes for each of the digits, I can then simply multiply them together. So for the first digit in Peggy's PIN, she can pick any number from 0, 1, 2, 3, 4 or 5. So there are 6 possible options for Peggy to choose. Looking at the second digit in her PIN, again Peggy can choose any number from 0 to 5, so another 6 options. Same for the third digit in her PIN, and also same for the fourth digit in her PIN. So now we know how many possible outcomes there are for each of these events. So for each digit in the PIN, we just multiply them together. 6 possible outcomes multiplied by 6 possible outcomes multiplied by 6 multiplied by 6 gives us a total of 1,296 possible pins that Peggy can choose from. So a lot of different numbers she could have chosen. Now moving on to the second part. Peggy decides to not repeat any of the digits in her pin. So in other words, if she has already used a 1, she's not going to use a 1 again, and so on. How many different pins can Peggy now choose from? So again, I'm going to put the dashes for each of the digits in her pin. 1, 2, 3, 4, and underneath I'm going to write down how many possible outcomes or options there are for Peggy this time. So the first digit, she can choose from 0, 1, 2, 3, 4 and 5, so there are still 6 options for this first digit. Now the second digit is slightly different this time. If she has already picked the first digit, then she has got one less digit to choose from for her second digit. So for example, if she's already used a 3, she now cannot pick a 3 again. So this time, rather than having 6 options, she has only got 5. We've reduced it by 1. For the third digit, it's going to be reduced by 1 again. There's only going to be 4 options for her to choose from. And then for the fourth digit, just 3 options left. So this time, because she's not repeating any of the digits, every time she has used a digit, the number of possible options for the next digit has been reduced by 1. Now we know how many options there are for each of the digits, we can multiply them together. 6 times 5 times 4 times 3 is equal to 360 possible pin numbers that Peggy can now choose from. So much less. So it's your turn to have a go at some questions like these then. Work out how many outcomes there are for each event and then multiply them together. If you are allowed to repeat digits, then the number of outcomes will stay the same, whereas if you are not repeating digits, then the number of outcomes will be decreasing. Pause the video to copy the notes, to check your understanding and to try the questions from I'm Building My Confidence. Remember to mark your work and reflect on your confidence. Unpause the video when you are ready to try the next question. Question 3. Sharon makes a 5-digit number. The number is odd. The first digit is 4. The middle digit is less than 7. How many different 5-digit numbers could Sharon make? So this question is quite similar to question 2, however we have got quite a few more constraints. Let's start by putting our 5 dashes to represent the 5-digit number. So without any constraints, the digits could be anywhere between 0 and 9, so single digits. However, let's take each of these constraints one at a time. So let's start with the number is odd. So if a 5-digit number is odd, then we just need to worry about the last digit, the last digit that makes the number odd or even, the number in the units or ones column. To make that 5-digit number odd, the final digit will have to either be a 1 or a 3 or a 5 or a 7 or a 9. So there are 5 options for the final digit. The first digit we are told is the number 4. So there is only actually one option for that first digit. The middle digit is less than 7. So that could be anywhere between 0 and 6. So 0, 1, 2, 3, 4, 5 or 6. That's a total of 7 different options for the middle digit. And then the remaining 2 digits, so the second and the fourth digit, we are not given any information about those ones, so they can take any value between 0 and 9. So for each of those, there are 10 options. Remember to count the 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 10 different digits. Now we know the number of outcomes or options for each of the digits, we simply need to multiply them together. One times 10 times 7 times 10 times 5 is 3,500 different numbers that Sharon could make. One outcome multiplied by 10 outcomes multiplied by 7 multiplied by 10 multiplied by 5 outcomes is 3,500 different outcomes all together. Let's have a look at question 4. Keith makes a 5-digit number using all of the cards below. Part A. How many different even numbers can he make? So again, let's start with our 5 dashes for a 5-digit number. 1, 2, 3, 4, 5. Now Keith wants to make an even number. We've got the cards 2, 4, 9, 3 and 6. So in order to make a 5-digit even number, there either needs to be a 2 at the end or a 4 at the end or a 6 at the end. So let's take each one in turn. Imagine we have got a 5-digit number with a 2 at the end. That means that for the other 4 digits we can use any of the other 4 cards, but remember, because they're on cards and he's using all of the cards, we can only use each one once. There will be no repeats. So the first digit, Keith will have 4 options to choose from. So all of the cards minus the 2 that he's saved for the card at the end. For the second digit, there will be 3 to choose from, 1 less than the digit before. For the third digit, there will only be 2 cards left to choose from. The fourth digit, there will just be 1 option left. And of course, we've got this 1 option with tied to having that 2 at the end there. So to make a 5-digit number with a 2 at the end, there are 4 times 3 times 2 times 1 times 1, 24 different ways that Keith can do that. The same will be true if he chose a 4 at the end. So 4 options for the first digit, 3 for the second, 2 for the third, 1 for the fourth, because we have got that 4, that 1 option at the end. So another 24 ways to make a 5-digit number, but this time with a 4 at the end. And then same for the 5-digit number with a 6 at the end. 4 times 3 times 2 times 1 times 1. So another 24 different ways. So now all we need to do to work out how many different even numbers he can make all together, we simply add the 24s together. So 24 ways to get a number with a 2 at the end, plus 24 ways to get a number with a 4 at the end, plus 24 ways to get a number with a 6 at the end. So 72 possible different even numbers he can make with those 5 cards, using each of the cards once and getting a 5-digit number. So we could have done this in a slightly quicker method. Again, let's put our 5 dashes for the 5-digit number. Let's deal with the final number first, because we are wanting an even number, and the even number, it's the number at the end of a number that determines whether it's odd or even in the units or ones column. And the only even numbers on these cards are 2, 4 and 6. There are 3 options for that final number. Now we have dealt with that constraint, you can go back to the first digit. Because we've chosen a number to get the end, that means that there will be 4 options for the first digit, then 3 options for the second, 2 for the third, and 1 left over for the fourth. And of course those 3 options for the final number. 4 times 3 times 2 times 1 times 3 again gives us 72 different even numbers that Keith can make out of those 5 cards, making a 5-digit number. Let's now have a look at the final question, part B. How many different even numbers greater than 50,000 can he make? So let's consider all of our options here then. So 5 dashes to represent the 5 digits. So the number has got to be, the 5-digit number has got to be greater than 50,000, and it's got to be even. So let's think about all of our options here. So for it to be greater than 50,000, we need to have either a 6 or a 9 at the front. So the first digit will either have to be a 6 or a 9. And then to make the 5-digit number an even number, we need the last number to be even. So if we've already used the 6 at the front, then there's only 2 options. You can either use a 2 at the end or a 4 at the end. Whereas if he uses a 9 to begin with, he's got a few other, well, he's got an extra option. He can pick either a 2 at the end, or a 4 at the end, or the 6 at the end. So if we take each one of these options in turn, let's have a look at starting with a 6 and ending in a 2. We've got 1 option for the first number, 1 option for the last number, and then in between we've got 3 digits that we can use, or 3 cards that we can use for the second digit. Then there'll only be 2 left for the third digit, and then only 1 left for the fourth digit. So 1 times 3 times 2 times 1 times 1. There are 6 ways of writing a number that starts with a 6 and ending in a 2. In a similar way, starting with a 6 and ending in a 4, we've got 1 option for the first and last digit, 3 options for the second digit, then 2, then 1, times. So another 6 different ways of writing a number that starts with a 6 and ends in a 4. And then same again, 1 times 3 times 2 times 1 times 1. Another 6 options there. 1 times 3 times 2 times 1 times 1. Another 6 there. And then 1 times 3 times 2 times 1 times 1. Another 6 options there. And then we can just add all of these together. So 6, add 6, add 6, add 6, add 6. There are 30 different even numbers greater than 50,000 that Keith can make using all 5 of those cards. Again, there is a slightly simpler method that we could use, but still a little bit fiddly, not quite as easy this one. Let's look at these 2 options here where we're starting with a 6 and ending in either a 2 or a 4. We've got 1 option for the first number, 3 for the second, 2 for the third, 1 for the fourth, and 2 options for the last digit, either a 2 or a 4. So we could have actually combined those into one calculation there. So 1 times 3 times 2 times 1 times 2, that's 12 different numbers. And then we could have combined these 3 here. 1 choice for the first number, the 9, then 3 times 2 times 1 times 3 for this one, because we've got 2, 4 or 6 we could have used there. So that's 18, and then of course adding the 12 and the 18 together still gets us 30 different numbers. So again, either method is absolutely fine with that one. So it's your turn now to have a go at some questions like these. Think carefully about the constraints, use those to work out how many possible outcomes there are for each of the events, and then multiply them together. When you have worked out an answer, make sure it seems reasonable. Pause the video to copy the notes, to check your understanding and to try the questions from I'm ready for anything. Remember to mark your work and reflect on your confidence.